All right. Hello, everybody. Good morning. Bright and early. And I get to talk about statistics. Yay. Actually, good for y'all. I actually abstracted away a lot of the heavy math stuff that I normally talk about. So there's just going to be a lot of pretty pictures of whales, because I really like whales. All right, so what we're going to be talking about is why is it so hard to determine where species are? And what we really mean is do species distribution models and mapping. And first we want to talk about, okay, we do actually need to understand the spatial distributions of our wildlife species, but also our plants, our other flora, fauna, fungi, bacteria, to understand biodiversity more generally. And because we cannot protect what we cannot measure. So we really do need to have that understanding for, our global sustainable development goals, 30 by 30, for protected areas, what do we choose to protect? But there's also a number of other decisions that are made around conservation. But it depends on, okay, do we think, these species of interest or these species that might be threatened, are they here? And the whole theme of this conference is amazing, especially you can see all the different groups who are presenting and all the different speakers. We live in this incredible, incredible time of sensors, technology, and tools, and data and computation, where we can actually identify species and their occurrence patterns through so many different technologies. So we have camera traps, we have acoustic sensors, we have eDNA, we have wildlife tags, there's satellite array data, and this is just to name a few. And then, of course, there's still humans in the field doing manual observations as well. So we live in this time where we have all of this information available, or that we can start producing at a huge scale. But sometimes, more data can be more problems. And there's also a lot of gaps still on where we observe and what we're observing. So we can see that, if we were to try to count the number of distinct species in GBIF, for example, like the distinct animal species that have been found in GBIF, this is from 2017, I might conclude that some of the most biodiverse regions in the world are the UK and maybe Norway, which that's probably not true, but that's where there was a lot of people who were actually uploading data to sources like iNaturalist or other citizen science platforms, and that's where where there's a lot more access to technology and a lot more access to, some of the different tools and platforms, or where population density just happens to be. And so we end up with a decent amount of records being produced, but they're also maybe reflecting some of the other biases in there around taxonomies and species of interest. Another issue is that, wildlife doesn't usually stay put. They move around. So even though they might be in one area, some have huge migration patterns and pathways, and some, within their local environment still move around, so they're not going to necessarily be in the same place at the same time of day, or even, 5 minutes later. And so it's very, difficult to say, okay, this is where the species habitat is when they're moving around, and so we might not see them at all. So how do we approach species distribution modeling and mapping? To really be honest, and as a statistician, I always say it depends. There's no one-size-fits-all approach. There's no perfect model. It's going to depend on what data you have available. It will depend on your sampling design. So how are you collecting the data? Are you doing repeated measures? It's going to depend on your species of interest, and we'll talk about some of those factors. Are we doing one species at a time, or we have many that we're looking at? But really the most important question is actually, what questions are we trying to answer? And that should be driving what our modeling or mapping approach should take. So this is kind of an oversimplification of some of the major types of species occurrence records that we get. Presence only, we have the location, the timestamp, and the species at a minimum. And so we know, okay, assuming there's no false positives or false detections, that this is where there was an occurrence of this particular species. Now, this type of occurrence record is often criticized for being fairly biased because we don't have where people were sampling and didn't find it. But one of the really nice things about presence-only data is that a lot of other data sources can be kind of reduced down, and so you can make that same assumptions about that sampling process because you have a timestamp, a location, and a species. And so a lot of data can actually be oversimplified into presence only, even though you end up taking away a lot of important information about what we call potential absences. Presence-absence data is the other most common record type, and so that's where we actually have marked potential absences. Now, the funny thing is, in my writing, I actually prefer using detection, non-detection as the terminology rather than presence-absence, because presence, yes, we can say, okay, it was here, assuming no false positives, but absence is maybe a little bit of a misnomer. Then we also have count data, and so you might have the number of distinct individuals when you're out in the field and sampling, or from whatever sensors that you're using. So these are kind of some of the broad classes there. But the reason I don't particularly like the language around presence-absence data is a lack of data or detection does not mean the species is absent. So first, we might have what we call the imperfect probability of detection. So just because a species utilizes this habitat, maybe it's even there, doesn't mean that we have a perfect chance of seeing it with whatever sensor or with whatever field observation what we're doing. We also have different biases in the records that are collected. We have an overabundance of records for certain types of species, like the charismatic megafauna. Large whales are sometimes easier to see, or humpbacks, they breach more, whereas beaked whales might not come to the surface at all and they go offshore. Or with birds, for example, we have a lot of different tools that make birding more accessible, and we have global communities of birders that interact with each other, so we have a little bit of a taxonomic bias there of overrepresenting bird records versus maybe some other groups. We also have that human density bias of where people are to be able to observe different species. We have temporal biases, one of which might just be there's a lot of less occurrence records at night when it's dark and people aren't out and about versus maybe in the mornings or during the daylight hours or during the clear weather events. And then, of course, we have other forms of spatial bias that might be related to that human density bias, more remote regions, or just completely inaccessible areas or areas that are really hard to observe. And so really, and this always is kind of one of the tensions when we deal with machine learning for wildlife technologies, is that there's oftentimes no real ground truth for wildlife occurrence, and specifically for those absences. So I prefer the terms for detection, non-detection as my data type. So when is an absence really an absence? These are all questions and not an answer, actually. So are we measuring during the time of day where the species is active? Do we have repeated visits to the same site? Are the individuals likely to be moving around, or do they stay put? How easy is it to be able to detect the species? Maybe it's a really, really small animal that doesn't move around and it hides out during the day and is only occurring at night. So therefore, the detection probability when I'm out doing a survey, if I'm at that time of day where it's the wrong time, maybe I'm not going to find it. And then, oh, sorry, that one got repeated. But then are we measuring during the appropriate season is another important thing, because for migrating animals, are they going to actually be, are we out there when they should be present? And so we have a bunch of different factors that influence whether or not we're going to see or hear or detect the species that we're trying to when we're out sampling. So then that motivates a bunch of different broad classes of models. And so this is probably the most technical part of, we have a few different types. We have the broad class of species distribution models that are often called habitat suitability models. And these are where usually using the presence-only data. And it's looking at the relationship with the background covariates, so maybe like temperature, elevation, and other, environmental things that kind of help define that habitat niche. And really what a lot of these are doing is looking at, okay, how similar are these locations to where we found the species? They're often criticized because, it's working with the bias presence only data, but the inferences can be valid for depending on your type of question. The occupancy models, on the other hand, generally assume that there's some sort of repeated sampling going on. So now you can actually separate out that probability of habitat use or occupancy from that probability of detection. And that's a really nice function. And then, of course, you have new emerging deep learning models that are often using the presence-only data because, again, it's a little bit easier to work with because of that sampling problem, and you don't have to deal with, okay, how do I format all of these different absences and at scale from all the different survey designs and for that sampling frame for the absences. So a lot of the deep learning approaches are really actually using the presence-only data, and they may or may not involve environmental characteristics, but a lot of them are using kind of the species, a number of different species simultaneously to learn about those joint distributions. So how do we know if our model is any good? In the machine learning world, we always talk about like benchmarking and like everybody wants to be the best. Well, I'm a statistician, so this is one of my favorite quotes. All models are wrong, but some are useful. And as a Bayesian, I always think about things in terms of there's always a certain level of uncertainty. And so really, it's not the right question of like, is this model any good, but is it actually any good for the kind of question that we're trying to answer? And so that's really where, you have to be motivated by the question and then mapping do you have the right data for that question to come at what's going to be the right model for understanding where they are. And so, there's those habitat suitability models, there's the occupancy models. Then we, of course, if you're lucky enough to have count data, you might be able to do some abundance or density models, or if you have other information like call density from your acoustic sensors or your satellite images, you might be able to actually get a lot of that information. A lot of times what we want to know is the range, so they're kind of broader area of usage in that kind of spatial extent of where they're found. Maybe we're looking at forecasting, and so we want to look at, predicted trends over time. And maybe what we're actually trying to do is improve our classifiers that work on our images or our sound data, and we want to kind of bound that by where is a likely area for the things that I've detected, so that way when I'm producing those classifier scores, I can kind of bound that, but I'm not making a major conservation decision. So you can see that it really depends on what you're trying to do with these kinds of data. And of course, every model is based on assumptions, whether it's statistics or machine learning. We have to kind of go through like what were we assuming about the data that informs that model. And then every model is going to have different strengths of assumptions. And so it's really important to think about what data is going into my model, how am I combining all of that information, and how strong of assumptions am I making with that information. But the models are better when we work together. What I'm not showing here is actually they can also be a little bit harder to disentangle. Yes, pun intended with the whales. That means that when we have a bunch of data and we have a bunch of information and we can inform each other, you can actually then start producing, potentially better, more valid models. And so when you talk to the local community, when you're using as much of the information and leveraging what you can, and then asking all of those right questions, that's when you can come up with more valid inferences. All right, that's it from me. Thank you so much, and this has been a wonderful conference so far, so thank you to our organizers, and thank you for everybody who's been participating and for who's developing all the technology that we can actually work with for all this work. Thank you.